This is part 5, the final part for transition metals and their chemistry. I'm excited to finish this topic, so let's start right away. So I'm going to be discussing catalysis in this video. So let's look at heterogeneous catalysts first. So these are catalysts that are in different phases from reactants, okay? And therefore it's easier to separate products from the catalyst. For example, you can use filtering from the reaction mixture. And the reaction occurs at the surface of the catalyst, okay? So which means that we need to look at this surface absorption theory. So first of all, what happens is on the surface of the heterogeneous catalyst, the reactants are going to adsorb, attach basically onto the surface of the catalyst, okay? Obviously, right? And the bonds within the reactants are weakened and the reactions are going to occur between them, okay? When I say bonds within the reactants, it doesn't mean that the A and B were bonded, okay? The bonds within A and the bonds within B, so you know how A and B could be a molecule with different atoms in there, right? So the bond inside A is going to be weakened and bond inside B is going to be weakened as well, okay? And then therefore reactions can occur between them, between A and B, okay? So the third one is the reaction can occur and then the reaction products are going to desorb, detach basically from the surface of the catalyst. So A and B has reacted and they became attached and then they are being released from the surface, right? So we're going to look at an example of a heterogeneous catalyst. In this case, we have the contact process. This is basically manufacturing sulfuric acid, the contact process, which is H2SO4, aqueous, and these are, it has many uses, for example, for making fertilizers, and that's just an example, but there are many other uses. We are going to be using the catalyst vanadium pentoxide, V2O5, okay? This is a heterogeneous, it's a solid catalyst. So one of the steps inside contact process, so this equation is not the whole contact process, but it's one of the steps inside the whole process. So we have 2 SO2 plus O2 giving sulfur trioxide, so sulfur dioxide plus oxygen going into 2 sulfur trioxide. So what happens in this reaction is basically the first step up to this reaction is the vanadium pentoxide reacting with sulfur dioxide, okay? When that occurs, we form sulfur trioxide and V2O4, okay? And V2O4 is going to react with oxygen to give V2O5 again. So V2O5 has been regenerated, okay? So if we add basically the two reactions together, then we can cross out V2O4 on each side and V2O5 on the different sides as well. So we will be left with sulfur dioxide and oxygen sulfur trioxide, okay? If you just times the whole reaction by 2, then we basically get the reaction that we started with, right? So that is the catalysis that vanadium oxide is doing. So the vanadium's oxidation state is changing from +5 to +4, and then because it's regenerated, it's changing back into +5, right? Yeah, that is an example of a catalysis performed by heterogeneous catalyst. And over here, catalytic converters in engines. So in engines, first of all, why do we need catalytic converters? The reason why is in engines, incomplete combustion of fuels may produce carbon monoxide. And we have discussed in part 1 why it's toxic, right? It binds to hemoglobin basically irreversibly, and it's going to disrupt oxygen delivery inside our body. And in high temperatures, in the engines is going to provide the large activation energy required for the nitrogen gas and oxygen in the atmosphere to react and produce nitrous oxides, okay? This X could be just 1 or 2. The reason why we have a large activation energy for them to react is basically because nitrogen has a triple bond, and it's therefore very strong covalent bond, which needs a lot of energy to break, okay? So this nitrous oxide gas is toxic, and also when it combines with water, it's going to cause acid rain, which basically is problematic because it's going to disrupt pH in the soil and water bodies, and they can also corrode buildings and other infrastructure because we have limestone, iron, or steel inside our building materials. Okay, so that is why catalytic converters help eliminate carbon monoxide and nitrous oxides, so we need them in the engines. Okay, so the catalyst that we can use is basically platinum, rhodium, and palladium in the engines. Okay, and basically what happens first of all is that carbon monoxide and nitrous oxides, if they form, they're going to adsorb onto the surface of one of these catalysts. Okay, and then the CO and NO bonds are weakened, so the bond between C and O and the bonds between N and O are weakened. Okay, so they are going to react. The carbon monoxide and nitrous oxide is going to react. So after they react, they're basically going to produce carbon dioxide and nitrogen gas. Okay, they're going to produce, and they're going to desorb from the surface because they are the products. Okay, this follows the surface adsorption theory, right? So the overall equation here is 2CO and 2NO. We get 2 carbon dioxide and nitrogen. And over here, yes, nitrogen is just 78% of the atmosphere. It's pretty much harmless. But yeah, you might argue that this is not completely good because carbon dioxide is still a greenhouse gas. But yes, it's still a greenhouse gas, but at least it's not toxic and it won't cause acid rain, which is more harmful in a way to us. So yeah, and next we're going to look at the homogeneous catalysts, okay? So as you can kind of predict, this has the same phase, same state as the reactants, and they form intermediate species, okay? So let's look at some examples. So over here we have the reaction, and in the reactants we have the 2 negatively charged reactants, okay? So which means that they will be repelling away from each other, okay? So therefore the reaction would require a large activation energy to overcome that repulsion, okay? So at room temperature, the rate of the reaction is going to be very slow, okay? Which means that we're going to use a catalyst. In this case, we're going to use an Fe2+ ion. So I have written the first step of the reaction, how it occurs. So this is going to react with iron 2+, giving us the sulfate ions with a 2- charge, and our Fe3+ ion is going to be generated, okay? If we look at the oxidation states, notice that the reactants now have opposite charges, right? So they're going to attract each other other than repelling, okay, instead of repelling. If you look at the oxidation states over here, sulfur has a +7, iron has +2, sulfur has +6, and iron has 3+. So it's a redox reaction occurring, okay? And now, when the Fe3+ is generated, it's going to come and react with iodide ions, okay, to form iodine, okay? And our Fe2+ charge, Fe2+ ion is regenerated. So what we started with is regenerated. Let's look at the oxidation state. Fe3+, obviously it's 3+, iodide ion obviously is -1, and Fe2+ is 2+, and iodine is an element, so it has an oxidation state of 0. So yeah, both of the products from the original equation are produced from the reactants, right? but it's just that the iron gave a different route of reaction that requires less activation and less energy. So that is giving a route that requires a lower activation energy. Okay, that was the definition of catalyst, remember? So yeah, we're gonna next look at the autocatalysis. This is basically the last catalysis example that I'm going to go through. This is a reaction catalyzed by one of its products. Okay, so when it produces its products from a reaction occurring, that one of that product is going to be the catalyst. Okay, so it's probably homogeneous, right? In this example, we have the manganate ion and the not chromate, the ethane dioate ion, and we have the H plus, and forming Mn2 plus, okay, and carbon dioxide and water. So let's look at this equation. So the reaction is quite slow to start with at room temperature, and even with a little bit of heat, it's still slow. And the Mn2 plus over here, the product, is the catalyst for this reaction, okay? So for normal reactions, if we plot the concentration of reactants against time, the graph will look like this. So the concentration of reactants is decreasing very, very fast initially, and then it decreases a little bit slowly as time passes, because our concentration of reactants is decreasing. So we have less reactants from the beginning, since the beginning. And yeah, as time passes, the concentration of reactants is going to decrease slowly until we've run out of reactants. Okay, so that is the graph plotted for normal reactions. So the gradient is going to be the rate of reaction, right? Because, gradient is just dy by dx derivation, and then that is basically the change in the concentration of reactants. The square bracket is concentration, by the way, and t is our time. Okay. So that is rate. That's the definition of rate, right? The rate at which the concentration of reactants changes over time. So as time passes, and yeah, this is basically what I just described. As time passes and more reactants are being used up, the frequency of collisions decrease, so rate is decreasing, as you can see in the gradient becoming less steeper. So I'm now explaining a little more with the collision theory involved. Okay, so for an autocatalysis reaction, you're going to see a graph that looks something like that. Okay, so it looks a little bit different. So this bit is quite similar, but this bit is different, right? So as time passes, rate is increasing because more catalyst, Mn2 plus, is being produced, okay? And catalysts, they speed up reactions, right? Yeah, so, but when we run out of reactants, the rate is going to decrease again because, the collision frequency is decreasing, okay? So yeah, that was autocatalysis and the end of catalysis and the end of transition metal chemistry. So if you were with me for these 6 videos, kudos, I'm proud of you. And I'll see you in the next video discussing a different topic.